which is a closed-loop data sense qualifier-based bus synchronizer to overcome convergence violations in clock domain crossings. I'll be presenting this myself, Bhargavas, and this work is also co-authored by Satya. We both work at Synchroniser. So just to clarify, since most of the sessions were related to formal, this is not the formal convergence that many of us were discussing about. This is convergence with the clock domain crossing violation. The discussion will go on as follows. Initially, we'll understand the motivation to perform this experiment. Then we'll see the main idea of how the experiment was performed, the evidence and use cases of it, and towards the end, we'll summarize the discussion. Coming to the motivation. Convergence is a commonly encountered clock domain crossing violation, which occurs when different signals are synchronized from their respective source domain to a common destination domain, and then they converge in the destination domain, leading to glitches and data coherency issues being propagated. So let us understand how convergence really causes an issue. If we look at the schematic, two data signals, data 1 and data 2, are synchronized using two flop synchronizers separately, and their synchronized versions converge in a combinational block, and then it is registered as data D. Let us see a scenario related to this schematic. As we can see in the waveform, data 1 gets asserted at timestamp 1 and data 2 gets reasserted at the same time. This is on the source domain side. However, on the destination domain side, due to delay in the synchronization, differences in the synchronization delay, data 1 was received at timestamp 3, but the data 2 took another clock cycle. Because of this delay, there is a possibility of glitches, one-cycle glitches being propagated, and also loss of coherency was observed between data 1 and data 2. This is to explain how convergence can cause an issue in simple words. The conventional way to analyze convergence violations is that we manually check if the sources which are converging are related to each other or not in the design. If we find that in the design these sources are not related, then we add a constraint to tell the tool to not check convergence among these sources. However, if it's found that these signals are related to each other, then we have to move the converging logic. In this case, the green color combo block that's mentioned would have to be moved to the source domain, and only the converged signal has to be then synchronized to the destination domain side. If this is not feasible in the design, then we have to add logic such that, say in this case, data 1 and data 2 are dependent on each other. Then we have to add logic such that this dependency is handled in the destination domain side and the function intent is met. The limitations with this kind of flow is that it requires addition of constraints for each and every violation, which is a tedious process, and it is difficult to update and maintain these constraints in complex IPs. And since there is also a manual analysis involved, this is risk prone. Adding constraints can also mask potential CDC violations in the future as well. So thus we need a solution to fix these convergence violations in the RTL. That brings us to the main idea of the experiment. So in any digital design, signals from different module hierarchies will be synchronized using different synchronizers, and then they will be routed to one common module where they converge. So the issue with this kind of synchronization scheme is that if there is any delay in the assertion or deassertion of one of these sources on the source domain side, that can propagate wrong logical interpretations on the destination side because of the different synchronizers that are involved. However, even if the signals were found to be unrelated and we have added constraints, say in the future some dependency was added on one of these sources, between one of these sources, then it can also mask those issues in the future because convergence will not be reported on them due to the constraints that are previously added. So hence this is not a scalable approach when it comes to, because of the risk that it causes if it's masked. So hence we need to ensure that we synchronize such related signals in such a way that convergence is not at all possible in the RTL itself. As opposed to the previous method where we had different synchronizers, in the current approach, all the sources that are related to each other and have the same source clock domain and have to be synchronized to the same destination clock domain are grouped together to form what is called as a clock group. Then all the signals belonging to the one clock group will be concatenated to form the data in bus input. This bus input is then given to the synchronizer. The synchronizer has a data sensing logic. It senses the change in the data input and generates a source domain qualifier. And this qualifier then passes to the forward qualifier path to the destination side. Once we receive the qualifier on the destination side, we generate an enable pulse, and this pulse acts as a enable to sample the source domain data directly in the destination domain side. Once the output sampling is completed, the qualifier is then sent back as an acknowledgement to the source domain side through the acknowledgement qualifier path. And once we receive this acknowledgement, once synchronization cycle is completed, and we sample new incoming data, and the second cycle begins. The data D output is then connected back to the destination module and used as how it was previously used. Now let us understand the synchronizer better with the help of a waveform. So as we can see in the waveform, the data input underwent a change from its whatever the value was previously to data 1. Now this change triggered the data as toggle qualifier to toggle, and this toggle qualifier is then synchronized to the destination domain side as data D toggle. When we receive data D toggle on the destination side, we generate a pulse out of it and use this pulse as an enabler to sample the source domain data, that is data 1, to the destination output, that's data out. And once the sampling is done, data D toggle return will be generated and it's synchronized to the source domain side and received as data as toggle return, which is the acknowledgement. Reception of data as toggle return notifies that one synchronization cycle is completed, and we sample new incoming data, that's in this case data 2, into the synchronizer, and we start the synchronization cycle again by toggling data as. So as we can see from the synchronizer that it uses a qualifier-based mechanism to synchronize the data path and does not actually synchronize the data path itself. So this ensures that convergence is not possible on the output bits and hence it can be safely waived on them. However, as I explained, the synchronizer does not accept new incoming data into it unless we receive the data as toggle return. So in order to ensure that the synchronizer does not lead to any data loss, the input is allowed to change only once during the synchronization cycle. And the next time when we receive the data as toggle return, it will sample the new data change. So this can be modeled using an assertion which says that until data as toggle is not equal to data as toggle return, the input can change only once. Coming to the evidence of how we did this experiment. All function related signals which were found in the design were grouped based on the source and destination clock domains into clock groups. And this bus synchronizer has been used to synchronize these signals, and corresponding convergence constraints on them have been removed. And the synchronizer has also been tested with a randomized number of cycles of missampling, and it has been proven to provide a convergence-free bus synchronization. As I explained in the block diagram of the synchronizer, the input is sampled only when there is a change in one of the bits of the input. So this will ensure that the synchronizer does not add to any additional dynamic power consumption, even in case of synchronization of quasi-static paths. So this table summarizes a comparison between different synchronization schemes that are available. So for a 64-bit bus, when the number of source and destination sync stages is configured to be 3 and the missampling is not enabled, in that case, for a multi-flop synchronizer, the number of flops that would be required to synchronize the 64-bit bus will be 192 flops, and the delay introduced on each bit is 3 destination clock cycles. The merits of using a multi-flop synchronizer is that it provides an simple open-loop synchronization, and it can be used when the source clock is not available or not known. However, using such a synchronization scheme can lead to data loss if the data stability criterion is not met, and it also causes loss of coherency, as I explained in the beginning. When it comes to recirculation mux-based bus synchronizer, the number of flops required would be 68, and the delay introduced is 4 destination clocks. The merits are similar to that of a multi-flop synchronizer. It provides a simple open-loop mechanism, and it can be used when the source clock is not known. However, apart from the demerits that comes with the multi-flop synchronizer, this synchronizer also requires an external qualifier to be provided. Now let us move on to the dual handshake qualifier-based synchronizers, which does not have the data sensing logic that I explained. So in this case, the number of flops required would be 136, and the delay introduced in completing one entire synchronization cycle is 4 source clocks and 4 destination clocks. The merits of using a closed loop mechanism is that it does not require an external qualifier. The qualifier will be internally generated based on the input. However, the demerits is that in this particular synchronizer, since there is no data sensing mechanism, the synchronization cycle keeps unconditionally running. So whenever we receive an acknowledgement, we start the next cycle, and upon completion of that cycle, we start the next one. Because of this, there will be additional dynamic power consumption even when the data input is not changing. And apart from that, the use of a closed loop mechanism adds to more delay than that of an open loop mechanism, and it cannot be used when the source clock is not available or not known. In case of the closed loop data sense qualifier-based bus synchronizer, which we discussed in the previous slides, the number of flops required and the delay introduced will be same as that of a conventional closed loop mechanism. The merits are similar to the conventional mechanism, but it does not add to any dynamic power consumption even when the data paths are quasi-static in nature. Coming to the demerits, it's similar to that of a conventional closed loop mechanism. It adds more delay and it cannot be used when the source block is not available or not known. Let us understand the use cases of the synchronizer. It can be used in two specific use cases. First one is register programming. Programming is a part of most IP designs. In our scenario, most of the convergence violations, around 70% of them that came up involved programming registers in them. Since the programming is carried out initially and then the registers are mostly quasi-static in nature, all the registers and the signals that are converging with them can be grouped together to form clock groups like I have explained, and the bus synchronizer can be used to synchronize these clock groups. This will ensure that the data coherency is met among all the bits that are converging. The second use case is a precision counter. In fast-running counters, it's a requirement that although intermediate values of the count is missed, whenever the count value is sampled, it should be accurate. In this case, the proposed synchronizer can be used because it will ensure that whenever the output bits of the counter are sampled, all of them are coherent to each other and the count value is accurate. Apart from these two use cases, we can use this synchronizer whenever in any non-timing critical data paths where coherency is a primary requirement. To summarize the discussion, convergence, as we understood, is a commonly encountered CDC violation which can lead to data coherency issues and glitches if ignored. We identified a problem in the conventional approach, that is addition of constraints, that it can mask potential CDC violations in the future, and it is difficult to update and maintain these constraints. As a solution to this, we saw the closed loop data sense qualifier-based bus synchronizer. It comes with advantages that it removes the occurrence of convergence entirely in the RTL itself, and it also removes the need to have convergence constraints as well. The limitations are the same as that of any closed loop synchronization scheme. It adds to more delay and it can be only used in non-timing critical data paths, and it has the input stability criterion to be met, that it can only change once during the synchronization cycle. Thank you for your patient hearing.
Any questions? Thanks a lot.